Cool. So I'm going to talk about tachytron and a recent extension of tachytron, capacitron. But in addition to talking about these specific models for speech synthesis, I also wanted to talk about some more general machine learning topics. So tachytron's autoregressive, and so I'm going to be talking about autoregressive distributions, and capacitron involves VAEs. I'm going to be talking specifically about VAEs. But I also wanted to just kind of have start with a very high-level discussion of the strengths and weaknesses of some of the different approaches to generative modeling, including autoregressive models and VAEs, but also including lots of other approaches. So I just thought it might be helpful to have an overview of the landscape. So that's what I'm going to talk about first, and then a little bit about tachytron and these autoregressive encoder-decoder models. And a little bit about loss functions, some stuff about KL versus reverse KL, which I think is something that's often overlooked in probabilistic modeling, or sometimes. And then I'm going to talk about variational autoencoders just from a general perspective, and then specifically how those are applied to capacitron. So kind of 3 machine learning topics and 2 speech-specific topics. Okay, so modeling high-dimensional data is a challenge in machine learning in general. So if you have a 10-second audio clip, it might be very roughly of the order of 1 million dimensions. If you have an image, a single like high-res image like is generated by some of the recent face generation GANs, might be 10 million dimensional. And just a short video clip could easily be 100 million dimensional. And this data is obviously, being natural data, has some structure to it. So there is some correlation across time or dimension for images. And there's correlations at multiple different timescales. So for something like speech, you'd have correlations because of the raw acoustics, the kind of sample by sample correlations. You'd have correlations at the level of articulator movement, at the level of phonemes, at all sorts of different levels. So what we'd like when we're modeling high-dimensional data is, I would say, a model that has generality. So it's powerful enough that it can capture the data distribution, or preferably any data distribution, and let's call that universality. I would argue, and this is less kind of widely accepted, that ideally we'd like it to be what I'm calling plausible, which means you want a model that kind of reflects our intuition about how the data was actually generated. And you could say, well, why would you care about that? But I'm going to kind of argue that maybe you do. And finally, that's tractable, obviously. Don't need to convince anyone of that one. It needs to be computationally support fast training and inference. And naturally, there's some inherent tension between those three different goals. So it's easy to think we're living in a real gold age of machine learning with neural nets, and we really are. It's incredible. But a lot of the generality, if you're talking about probabilistic modeling, so let's say we're talking about P of y given x, and this could be speech to text, text to speech, machine translation, all sorts of things. A lot of the early successes in particular, So we have a huge array of tools for coping with the situation that X, the thing you're conditioning on, is high dimensional. So DNNs, CNNs, dilated convolutions, RNNs, highway residual nets, attention and transformers, all are very flexible tools that we can mix and match to get flexible dependence on X in a neural net-based probabilistic model. We can mix and match those according to our intuition. So, you know, how they should be, if we think X is a sequence, so it's natural to have some thing that picks up on some specific correlations we expect to be there, you know, we can design the system architecture with that in mind. But in contrast to the situation with the X, the thing you're conditioning on, the thing you're modeling, Y, Some of the most striking early successes in that modern era, let's say post-2006, had very simple Ys. So AlexNet, ImageNet, there's lots of CFAR systems, the early DNN and LSTM acoustic models for speech recognition, the systems for speaker recognition and face recognition, all had very simple outputs, typically just a discrete 1 of k output. And in that case, it's very easy to come up with a probability distribution that captures the generality aspect completely. It's just a categorical distribution. So stick a softmax on the end of the neural net, and you have a model that's flexible in terms of both P of y. The model P of y given x is flexible in terms of both y and in terms of x. So that is a great situation if the y is not too complicated, but capturing that generality is harder when y is very high dimensional. So some highlights from the current kind of toolbox for this side of things is independence. So it's often not completely ineffective to pretend things are independent, even if they're not. For instance, when we're recognizing speech, we might assume that the conditional in the entire waveform, the phoneme at time 1 and the phoneme at time 2 and the phoneme at time 3 are all independent of each other. And that doesn't work too badly, even though it's clearly not true. Another is mixtures. So I include that mainly just because in principle, mixtures of Gaussians are universal. So that's kind of a simple example of a universal model, meaning that, finite dimensional, they can capture any finite dimensional distribution with enough parameters, a GMM can capture it. Autoregressive, that's something that's been extremely fruitful in the last 5-10 years. So we've seen all sorts of examples of that. I'll talk about examples in a minute. Another trick is having an observed intermediate representation. Let's say if we want to go from text to waveform, we treat the MEL spectrogram, which we extract from the waveform, so it's strictly a function of the waveform, but we pretend that it's kind of a latent on the way to generating the waveform. So that's helpful. And finally, there's the 3 kind of recent developments in generative modeling, VAEs, GANs, and flows. And yeah, VAEs end up with an upper bound kind of thing, or depending on whether you're talking about the negative of the log probability or the log probability. GANs end up with a lower bound, and flows are a bit different. They have this sequence of invertible transforms to warp a base distribution. So there's certainly loads of progress in recent years. This is incredible in lots and lots of ways. But this toolbox is nowhere near as rich, as composable, as flexible as for these high-dimensional Y cases, the high-dimensional thing you're modeling, as for the high-dimensional X cases, the high-dimensional thing you're conditioning on. And it's a lot harder to mix and match. You have to worry all the time about whether things are normalized as probability distributions, and just in general, you can't just combine things any way you like, the way that you can with the X side of things. So assorted examples of, I thought I'd just go through a few examples of recent successful models with high-dimensional Y, and then how they kind of fit into that classification. So early DNN and LSTM acoustic models for ASR and TTS just assumed independence over time during training, at least. CTC acoustic models also assume independence over time, and they've been very successful. Mixture density networks for TTS, I believe all of the early stuff was independence over time. I'm not sure whether it's ever been done autoregressively. RNN language models are autoregressive, and specifically autoregressive using an RNN. And as I said before, this is going to be a very high-level discussion, so I'm not going to go into details of exactly what autoregressive means. In that particular case, we'll see it later, but I hope it's still helpful anyway. Then we have listen, intend, and spell, deep speech and deep speech 2, which are again autoregressive using an RNN. And really, from the point of view of the output modeling, there's very little difference between RNN language model, listen, attend, and spell, tachytron, car to wave. They're all just autoregressive using RNNs. Then we have Deep Voice 3 and Clarinet and Pixel CNN, which are autoregressive but using CNNs as the way to summarize the state going from one time step to the next. And Pixel CNN in particular is a model that I think is interesting because, you know, it's clearly a bit of a not following the generative process of how images are really generated, so it just operates in raster scan order, just filling in pixels as an old television screen would. And it's still able to compress images really well. So, yeah. And then we have things like WaveNet, that is also autoregressive, but now using dilated masked convolutions. Sample RNN and Wave RNN are autoregressive using RNNs, so we're seeing a limited set of tricks here. MELNet is autoregressive using RNNs with an unconventional scan order, which kind of generates a low resolution grid of time frequency features, observed features, and then gradually kind of infills that to higher and higher resolutions. Then we have transformers, and they've been used for machine translation and ASR and TTS. And those are autoregressive, but instead of using RNNs or CNNs, using masked attention, which again is really about the X that allows them to be more, well, anyway, okay. And then we have things like BERT, which arguably, if you view it a certain way, is autoregressive using transformers with a randomized scan order. Fast speech has recently come out, and it is, as far as I can tell, is non-probabilistic. It's not, it doesn't really have any natural probabilistic interpretation. VQVAE and the recent VQVAE2 paper that generated incredible face images and other images with a VAE with much higher fidelity than had really been done before. And that uses VAEs, so now we're starting to get into the more recent theoretical developments. Progressive GAN and style GAN were both extremely impressive papers and use GAN also plus the other trick of these observed intermediate representations. Big GAN and GANsynth use GANs. Parallel WaveNet uses a flow, specifically a inverse autoregressive flow, so an autoregressive based flow, I've called it. Clarinet, the kind of second part of it, is an autoregressive based flow, and GLOW and WaveGLOW are convolution based flows. So, you know, there's definitely some variety in terms of what's been successful, but equally there's like a few nails or a few hammers. I don't know quite what the right analogy is. But yeah, definitely autoregressive models being used all over the place. So the different approaches have different strengths and weaknesses, and frequently there's a tension between the generality. As I said before, is the model capable of capturing the true distribution? Is it universal? Plausibility, the form of the model we'd like to use based on our intuition of the actual generative process, and tractability, does it allow tractable inference? So how do these different approaches, independence mixtures, autoregressive, etc., compare on these different axes? I just thought it might be interesting to take a very high-level perspective and say, you know, go through them one by one. So independence is clearly terrible on generality and plausibility for many applications, fantastic for tractability. Mixtures are kind of okay for generality, usually pretty poor for plausibility unless you've got very particular type of data. They're good for tractability. but they're theoretically universal for fixed dimensional distributions, meaning they can represent any reasonable distribution given enough parameters. And in practice, that doesn't really mean very much, and they're incredibly parameter inefficient. They require a huge number of parameters in really high dimensional spaces to do well. And I'm going to argue maybe like it's the same thing with some of the more modern methods as well, possibly. Then there are autoregressive models. So they are pretty good on generality. They're usually poor for plausibility and often good for tractability. They're also universal in a slightly different sense from the mixtures. So if the individual, so an autoregressive distribution is made up of a series of one-step ahead predictions, and if those one-step ahead models are each sufficiently general, then the overall sequence level model is general. So the initial kind of decomposition that we're going to see more later that autoregressive models start from is making no assumptions, which is a really nice property. But that universality doesn't, always translate or that theoretical universality doesn't necessarily mean much in practice always. And in particular, if you're using an RNN or CNN, then there's a limited effective memory, and attention is a great solution to that. In terms of plausibility, for modeling images, it's very clear, as I alluded to briefly earlier, where the pixel CNN, which is generating pixels in a raster scan order, is very far from the actual generating process. So certainly some autoregressive models are clearly not plausible. For ASR and TTS, at least the text and audio is inherently sequential, so you might think an autoregressive model is much more natural in that case. But generating, let's say, one waveform sample at a time still doesn't really capture the time resolution, things happening across multiple time resolutions. So I'm thinking of kind of the semantics happening at a relatively slow pace, and then syntax inducing correlations over a shorter time scale, but still relatively long. Words induce correlations over very short time scales compared with semantics, but still long compared with other things. So, and then you can go down over time scales through phonemes, articulators, and then acoustic physics getting shorter and shorter. So, yeah. Okay, observed intermediate representations are very domain-specific. VAEs, the first of the three kind of modern generative modeling approaches, are okay for generality. There's some limitations to them, as we'll see later. And they're often pretty good for plausibility. They would be fantastic if it wasn't for some issues with the variational posterior. And they're often pretty good in terms of tractability. So the generative model in particular can be made very general. Even if your individual pieces that you're building the generative part of the VAE from are very simple, like distributions that are independent over dimensions, you can still get a very complicated overall marginal distribution because of the dependence on the latent of the observed value on the latent can be very complicated because we know how to do things that are complicated on conditioning, the thing they're conditioning on X in the previous slide. So the generative part often has good plausibility too, so we could use phonemes as a lower time resolution latent that's not actually observed, but we think is there for the waveform, for example. The variational part is more problematic though, so VAEs have a generative part and a variational part, as we'll see later. And independence is often used in the variational part as well, but here it's like a little more, I don't know, causes some more problems. And if you want to get really good generality of the overall model, that variational posterior ends up having to be really general as well. And you have to use some universal model like mixtures, autoregressive models, or flows to do that. And that's been very successful, and that definitely has leads to improvements, but you risk maybe having to use a lot of parameters if it's not actually a very good plausible representation of the actual posterior, perhaps, you know. And then, yeah, at a high level, the main point is just that a non-universal variational part can have complicated consequences for the generative part. So it's not just that the variational part gets thrown off, but that can have knock-on consequences on your estimation of the generative part. Finally, we've got GANs and flows. So GANs are absolutely fantastic in terms of generality. I mean, literally GANs are composable in the way that the dependence on X is. You know, you can just have any stochastic function you like, put them together in any arrangement. So you could generate one thing over here, combine them in a very flexible way, then add some extra noise from somewhere else, and then, you know, completely general combination. And because of that, you can also make them highly plausible. So you can have things that really emulate whatever you think the real generative process might be, or captures elements of whatever you think the real process might be. They're trivially universal. I mean, anything that you can compute with stochastic functions, you can, that's just your generator. But the training is challenging due to stability, mode collapse, stuff like that. And finally, we have flows. So flows are decent in terms of generality. I've said not great in terms of plausibility usually, and decent in terms of tractability. I presume they're universal. I don't know of any theoretical results, but I mean, well, I guess there are anyway. But it seems like it must be the case that they can represent any reasonable fixed dimensional distribution given enough stages of flow of a suitable type. But we're not free to represent, if we have some intuitions about how the actual generating process works, we can't directly encode that if it involves non-invertible operations in the flow. I mean, maybe in some cases you can imagine that gradually warping the space distribution might be a plausible generative mechanism. But, and especially for flexible flows like these neural ODE flows. But, you know, it's still somewhat limited. And decent tractability depending on the details of autoregressive versus inverse autoregressive. Fundamentally, though, they're tractable. So generality and tractability are natural to care about, as I said, but who cares about plausibility? And I don't know, this is really conjecture. Maybe I'll be wrong about this, but I suspect we pay for lack of plausibility by requiring more parameters. So if you use a model that's universal, but doesn't reflect the underlying generating process, you probably end up having to use lots more parameters than you might have needed if you'd modeled the underlying generating process more directly. And you see this empirically for face generation with GANs versus flows. The flows get amazing results, but they need a lot of parameters to do so. Whereas the GANs, which you could say perhaps represent a more plausible model of how images might be generated, where they kind of generate a low-res thing and successively add noise and upscale. You know, maybe that's more reasonable, and they use fewer parameters. And certainly, if it was the case that the actual generating process consisted of latents at multiple time resolutions, then you can easily see how an autoregressive model might require loads of parameters. So for an RNN, it has to remember lots, but even if you're doing a transformer, the model still has to effectively be inferring all the stuff it needs from the latents, at least as far as they affect the output distribution at every time step. So it kind of has to infer the latents, then given those latents, sample a new output, then given that output, re-infer the latents. It can't remember the value of the latents that it effectively constructed at the previous time step, because it has to route all of its dependence on the previous time through what's observed. And that's possible because they're universal, but potentially the network would have to be doing all sorts of contortions in order to make that happen, conceivably. Okay, so that's the summary of this kind of high-level view that I wanted to present. So I just think it's worth bearing in mind maybe that despite the set of kick-ass tools for allowing dependence on X for P of Y given X, we don't really have great tools or as general tools for modeling high-dimensional Ys in P of Y given X. Yeah, it'll be interesting to see how this changes in future. But yeah, so that's the end of the first of the 5 segments. And yeah, any questions so far?
So my question is, you discuss about different architectures and different, let's say, models. How about the internal representation, like how many layers, how many units, how this is affected the results on each of these models?
Yeah, I mean, I'm kind of assuming that all of the lower level details are optimal or as good as they can be, and looking more at the fundamental limitations of the different model architectures. So for an autoregressive model, it doesn't matter how many layers you have in the autoregressive modeling, it's still fundamentally limited by certain aspects of the fact it's an autoregressive model. But in practice, obviously, those things are massively important, and I'm not downplaying them. This is just, I guess, an alternative high-level perspective.
Matt, may I ask you also a question? Thank you very much. That was really very nice summary of this probabilistic modeling in the context of neural approaches. And you mentioned the 3 categories. Usually also people try a plausibility. You said, okay, who cares? But if you don't care, probably we use more parameters to cover. People try to interpret also the results, even if you assume a certain model and you put it in action. Even if you think it is plausible, still you have to interpret somehow the outputs, somehow not so much the output, but the structure inside, in order to see if indeed it does what you expected the system to do. So is it a 4th dimension, like the interpretability, that we could add to that the triples that you had?
Yeah, I think so. That's definitely something that people care about, and for good reason. Yeah, I think so.
If that is the case, that we had, let's say, 4th dimension, you think that any of these approaches offer more intuition or more information that we can interpret them, or there are some of the structure that are easier to interpret than others?
I mean, I guess there is an interesting thing there with GANs versus VAEs, just in that even if the GAN is a very accurate generative model of, captures the true generating process very well, you still can't look at a real image and say what was the value of this parameter used to generate this image. Whereas VAEs, you can do that inference over the latents. So in that sense, VAEs might be easier to interpret than GANs. Just great. Okay, so coming back down to more concrete stuff for a little bit, I thought I'd briefly review Tachytron. Vasilis reviewed Tachytron yesterday as well, so I'm going to go fairly quickly through this, but I guess at least I'll be looking at it from a specific perspective, which is the decoder and the autoregressive nature of the decoder in particular. So the core of tachytron is a probabilistic model P of y given x, where y is the Mel spectrogram and x is the text. So either a grapheme sequence or a phoneme sequence, something like that. And both x and y are high dimensional, so we're in that setup that we were considering at the very beginning. And it uses attention for flexible dependence on x. That works really well in general for lots of models. And the autoregressive decomposition is used specifically on RNN for flexible, capturing a flexible distribution over y. So it's a particular form of encoder-decoder, or some people call them sequence-to-sequence models. Other models, such as jointly learning to align and translate, the model from that paper, or the listen, attend, and spell model, so for machine translation and speech recognition, respectively, are basically the same as tachytron modulo some details. They're both encoder, attention over the encoder from the decoder, autoregressive decoder, and specifically recurrent autoregressive decoder. Yeah, I also just wanted to start drawing some graphical models. So tachytron, very simple graphical model here. I'm drawing nodes as circles if they're observed variables that we're modeling. Nodes as little dots if they're things that we condition on, so we're not modeling. And so this is, the graphical model in this case is P of y given x. So this graphical model is just encoding the same thing as writing P of y given x equals P of y given x. So it's not particularly interesting, but it kind of might be helpful to refer back to this as we add nodes. Okay. So the autoregressive decomposition over y that is at the base of that big list of models that use autoregressive decoders or autoregressive modeling of some sort is as follows. P of y, I'm sure you've all seen this before, P of y given x is the product over time of P of the y at time t, given all the previous y's, and the entirety of x. So this decomposition, sometimes called the product rule of probability, it's completely general, and any probability distribution obeys this factorization, but that doesn't mean that parameterizing these individual factors in a certain way is necessarily natural, or it could be natural or not for a given application. For tachytron specifically, for the component distribution at each time step, the dependence on the previous y's is with an RNN, and the dependence on x is with attention. So there's a great explanatory figure of this in the listen, attend, and spell paper. This is the clearest description, like kind of minimalist description that I've found of these general autoregressive decoders using attention. Yeah, so if we zoom in first on the encoder part, which I won't focus on too much, this is quite different from the one used for tachytron, just in the sense that it reduces the time resolution as you go up the stack. But anyway, let's move on to the decoder, since that's more similar to tachytron. You can see that there's a number of pieces. So at the bottom here, we have the attention RNN, and the attention RNN is outputting some particular query that it would like to ask the attention mechanism to look up in the input sequence. And so on the basis of, for example, taking the dot product of this query vector with all of the individual elements of the encoded text sequence, it'll spit back essentially just one of those elements, an average of a couple, but in practice, if attention is working, it just ends up being one element of this encoded input sequence, and that then gets fed into a stack of RNNs, here shown as just one layer, but in practice in tachytron there are two layers of this decoder RNN, and that takes all of the information that has gone into this point and does extra kind of sequential processing. So the information that's available here is all of the previous time steps summarized in the attention RNN state, but depending on the exact details of the model architecture, maybe that can only affect this point through the query that it, or through the glimpse that it returns back from the text. Anyway, and finally, after the decoder RNN stage, we have this output distribution, which outputs the parameters. It's just a deep neural net or a feed-forward neural net that outputs the parameters of the distribution over the y at time t. So at a high level, we're at each time step, we're taking yt minus 1, feeding it in, and getting out a distribution over yt. Another detail is just that the attention glimpse, the single element of the text sequence, the encoded text sequence that's fed into the decoder RNN is also fed back into the attention mechanism or the attention RNN. And that's important because otherwise the attention RNN would have no way of having dependence on the text. It would only be able to have dependence on the audio via the wires that are fed directly into it. And so obviously you can imagine it might be helpful to have this RNN that's deciding where to look also have seen the text that it's deciding where to look within again. Okay, so that's broad stage tachytron decoder. I've said lots of this already, but so the decoder is autoregressive and consists of an attention RNN, an attention mechanism, decoder RNN, and then an output distribution. The glimpse output by the attention mechanism is fed back into the attention RNN, as I mentioned. So the RNN state that we're passing from one time step to the next is the attention RNN state, the thing that the state associated with this RNN. The previous glimpse, so this glimpse is being fed back in to the attention RNN, so that needs to be kept in the overall state. The decoder RNN state, I realize I've defined this recursively, the decoder RNN state consists of the decoder RNN state, but I guess we're talking about the broad decoder and then the specific layers of the decoder RNN. And then there's some attention mechanisms that also have an internal recurrent state. But yeah, that's the kind of high-level architecture. I guess I'll just briefly pause to see if anyone wants to have questions. I know this is something that's often hard to understand. I find it hard to understand. So just if anyone has questions specifically on this.
What is the output distribution? Is it like in the vocoders a softmax or something different?
Yeah, I mean, for this specific paper, it's speech recognition, so it's a distribution over characters, like this diagram. But for tachytron, it is the Mel spectrogram frame. And I'm phrasing things very probabilistically because I think it's a helpful way to look at things, but tachytron actually uses an L1 loss in practice. You can view that probabilistically as a kind of Laplacian distribution, but I guess in terms of what tachytron actually does in practice, usually it's just the L1. So it just outputs a single value, and you're minimizing the L1 loss of that value to the target. In terms of a helpful way to view it in general, it could be any output distribution. It could be a multivariate Gaussian, a mixture of multivariate Gaussians, some more complicated thing that's autoregressive just over the individual components of that spectral slice. You can do lots of different things.
But still it will be one single output. It's just the loss function that changes, and based on that you have the likelihood function.
Yeah, I mean it's I guess an easy way to think about it is you're always using the log likelihood as the loss function, and the only thing that's changing is the distribution, the model itself. So whether you use a Gaussian or a mixture of Gaussians or Laplacian or whatever. Does that answer your question at all? Sorry.
How is the context vector passed into the next time frame?
It's just concatenated to the, you mean what I've called the glimpse, like this C1 here? It's just concatenated to the input to the attention RNN?
Because you have it like it goes with the hidden state.
You're right, yeah. This diagram is surprisingly good, but I suspect that aspect, I mean, maybe that's what they did. That wouldn't make a lot, well, I mean, it's all the same really. Okay. And then, so in addition to the encoder and decoder, the decoder just gets us to the MEL spectrogram. There's also the vocoder, and in the original tachytron, that was a learned postnet mapping the MEL spectrograms output by the decoder to linear spectrograms. And then you have a iterative Griffin-Lin algorithm with no learned parameters to go from that linear spectrogram to the waveform. And more recently, the tachytron 2 style way of doing things is to use a wavenet or wave RNN trained to go from the MEL spectral outputs to the waveform in one step. Note that that's a little different from the very original WaveNet formulation where it was taking linguistic features as inputs, kind of going all the way from a time-aligned representation of the text. But yeah, that, as several people have alluded to already this week, that works really well. Just as a detail, there's a stop gradient, so the vocoder doesn't affect the decoder training. So you're training the decoder to do well with whatever the decoder happens to, you're training the vocoder to do well with whatever the decoder outputs, but it's generally not the case that the vocoder training affects the decoder training. And the postnet and Griffin-Lin is very useful for fast iteration. Obviously, the Wavestar stuff is much better quality, yeah. And here's the...
excuse me,
Sorry.
one question, sorry. Have you tried to use other type of acoustic features to predict, like for example, standard vocoder features like spectral envelope?
Yeah. So I actually only joined the tachytron team relatively recently. Before I joined, I think they did try some experiments in that vein. It was one of the first things that I wanted to know because I did my PhD in speech synthesis around 2013, 2014, and in those days, I thought the kind of received wisdom was that you're crazy to try and model a spectrum which has periodicity in it if you can get rid of that periodicity with vocoders like straight. And it's, you'd expect much better performance if you model F0 separately and the spectrogram with periodicity removed separately. Yeah, all I can say is I guess they didn't find that gave improvements in this case, but
Okay.
The spectrogram computed directly with the STFT does have the advantage that it's really simple, and if the recent kind of neural models are sufficiently powerful, maybe they can cope with that anyway. I mean, clearly they kind of can, but yeah. What are your thoughts?
I'm just curious about the results by using a standard vocoder like straight instead of using Griffin-Lin, for example.
Yeah. Yeah. It definitely doesn't work better than WaveNet.
Yeah, I guess. Thank you.
So this is the original tachytron architecture, and I guess just a couple of details with this that didn't present before. There's a prenet which summarizes the frames that are coming in. It actually acts as a kind of bottleneck to restrict the amount of information that can flow from previous frames into the current frame, previous output frames. And one of the intentions, I believe, with that is that it's actually could be a bad thing if, in terms of getting the decoder to pay attention to the text and actually use the attention mechanism, it could be a bad thing if there's too much helpful input from previous outputs. It could easily, if you just take the previous output and repeat it, that's a pretty good guess at what the current output is, because spectrograms change relatively slowly over time. And so you might imagine that sometimes it fails to pay attention to the text. Presumably that is not as big of a problem if you've got a good attention mechanism, but yeah, that's my understanding of the situation anyway. Another detail is that often there are these stacks of frames that are predicted all at once, and that helps in a couple of ways. One is the decoder doesn't have to remember for as many time steps. In a kind of trivial way, if you're grouping 3 time steps together, then the recurrent state has to go through 3 times as few non-linearities in order to propagate from a given time index to another time index. And the other aspect I've forgotten, but it's in the slides in a moment. Yeah, I think that was all I wanted to say about that architecture. Then there's Tachytron 2. That yeah, is in terms of broad architecture extremely similar. There are some minor details, minor ways in which it differs, but the big difference is using the WaveNet on top. Another improvement is using the stop token. So the original Tachytron just kind of generated for a fixed amount of time, and obviously it's nice to have the model decide for itself when to stop. That's fairly easy to do. You just, as well as outputting the current frame, output a decision as to whether to stop or not, and you essentially just train that using maximum likelihood. And that fits very well within the autoaggressive nature of the decoder. As I mentioned earlier, I presented everything probabilistically, but in practice, usually an L1 loss is used. Even though it's using an L1 loss, teacher forcing is used. So you could view, it would be natural to view L1 as the log likelihood of a Laplacian distribution, which has isotropic and constant over time scale parameter. So a very kind of dumb Laplacian distribution. You wouldn't expect it to be a good probabilistic model as a probabilistic model. But you can also use true probabilistic models as the output distribution. That works. And as I mentioned before, there's this detail with the reduction factor. I guess I just had that it was helping the alignment potentially as well as the decoder memory. Prenet I've already talked about. So teacher forcing I've already mentioned, but I didn't really define what it was. So at training time, the ground truth spectrogram frames are fed as input to the decoder, and that's referred to as teacher forcing. At synthesis time, we feed the previous spectrogram frames generated by the decoder as input to the decoder, and that's non-teacher forcing. And that might appear to be inconsistent because we do one thing at training time, one thing at synthesis time, but at least if you're doing things probabilistically, it isn't, and I'll discuss that a bit more in the next section. And then, so to summarize this kind of Tachytron section, an encoder-decoder model for text-to-mel spectrogram generation. Tachytron is, an encoder-decoder model for text-to-mel spectrogram generation. And it uses an autoaggressive decoder backed by an RNN, attention over the encoded text. And there's a really fun demo page. I'll play some selected examples later just for capacitron, but if you haven't been to the page and played around with it, like, it is quite fun. I found it fun the first time, so I'd recommend it. Yeah, so any questions about the tachytron part?
So I wonder if you will talk more about the synthesis and training mismatch. Means if you, in a synthesis, if the prediction is error, then there is no chance for the model to recover to...
Yeah, I will talk lots more about that, actually.
I think for me, one of the great things of these models like tachytron, comparing them to normal DNN TTS, is that if you train them with really expressive data, you get out the same kind of expressiveness, while with the DNNs, you kind of got everything like flat, right? You didn't get the same pitch out, it was just sort of averaged. What part of all this architecture do you think is responsible of that? Is the architecture, is it that we have an attention looking at everything? Is it the encoder, is it the loss? Like, what do you think?
Yeah, that's a really great question. I mean, I don't know, but so do you think that for instance, the variability in the F-zeros wasn't as large as it was in the original? Is that one of the symptoms? Like the F-zero trajectories were getting averaged, and so you'd lose the big highs and the big lows? Or?
That would happen, like, for example, when you train with Merlin, with just like a feed-forward DNN, right? Mm-hmm. The SPCC. That's what we would see, right? Yes, like in your training data, maybe you had like very good pitch going up and down, but then when you synthesize, you would have something more flat or plain. But now with these models, we can see that, or in my experiments, I don't use exactly tachytron, but it's systems like tachytron, which is DCTTS. You get out the same expressiveness that it was on the training data.
Yeah, I mean, and there should be still, at least for the vanilla tachytron style thing, like the L1 loss. I don't know if you also use an L1 loss, but there should be still some averaging, at least of the individual conditional distributions of the current frame, given everything that's come before, that will still be averaged. And like my intuition was that was probably really bad, but it doesn't seem like it seems to work. I guess if you have really flexible dependence on the past, and there's enough correlation between the past and the current kind of thing, then there might be enough information in what you've decided to output already that to have a very peaked kind of decision. Like, let's say the F-zero is flat for a while and then could either go way up or way down with 50-50 probability, just depending on how the speaker was feeling on that day. You know, if you just take a model that is non-autoregressive, that just considers each time slice independently, and it ends up being trained with an L1 loss or something, and so just averages, you'll get just an overall flat trajectory. Whereas with the autoregressive models, sure, it'll model this bit well, it might get something a bit wrong as you start to go diverge, where it averages a bit, but eventually it'll start to go down one path or the other, and then it can be nice and confident in going all the way down that path. So I don't know, that's a rough.
Okay, thank you.
Great. Yeah, and it's just in terms of breaks, is it? I personally...
It's absolutely up to you.
Okay.
I mean, if you want, you can make a break now, and then we continue.
Can I do 2 breaks in the 3 hours?
We can have more than
Great.
2 if you want. It's up to you. You are the king.
I just personally, I mean, I've heard people kind of tune out after 25 minutes. That's about the longest anyone can really pay attention for.
So we can have a break.
Let's have
Yes,
a break now.
great.
Right, so the third of the 5 topics that I wanted to talk about is loss functions. We talked a bit about the choice of models, but the choice of loss function also matters. And in particular, I wanted to outline some implications of training with different loss functions and especially focusing on autoregressive models like tachytron. And yeah, this is relevant for general machine learning. I mean, I'm interested in this from the perspective of speech, but it's definitely more generally applicable as well. So firstly, just I wanted to mention in passing non-probabilistic loss functions. Sometimes, for example, if I've understood the fast speech paper correctly, that one, and minimum generation error training back in the day, the overall sequence level L1 or L2 loss is used for training. So your model deterministically produces some output. That output is a sequence, and then you take the L1 of that entire sequence to the targets. And this has a theoretical disadvantage that I just think is worth maybe being aware of. You know, that I'm not saying this method won't ever work in practice. Like, clearly it works very well in some cases, but it's just worth being aware of this. And this comes back to the discussion of averaging that we were talking about a minute ago. So it's well known that the minimizer of the L1 or L2 loss with respect to a distribution is an average. For the L2, it's the mean of that distribution, and for the L1, it's a kind of spatial median. Like in one dimension, it's the median, and in multiple dimensions, it's some generalization of the median. And that means if you have a speech synthesis system which maps text X to spectrogram or waveform Y deterministically trained with L1 or L2, the best the system can ever do, if it had infinite data, infinite time to train, infinitely flexible model, is to output the true average spectrogram or waveform for that X. That is, if you got someone to say the same text lots and lots of times and average the result, so same X input, average the result to the outputs, that's the best that that model can ever do. It can capture the mean perfectly. That's all it can ever do. And this might not be, depending on the application, exactly what you want. So the average of a spectral frame with an F0 of 100 hertz and one with a F0 of 150 hertz is not a spectral frame with an average of 125 hertz. It's an incoherent mixture. Just in case that isn't clear, draw a little picture. So if you have a spectrogram with some, let's say linear spectrogram with some periodicity like this, at, say this is 0, so 100 hertz, 200 hertz, 300 hertz, etc. We have another one that's at 125 hertz. And we take the average of those two, we don't get something that has 112.5, I'm changing my numbers, but you know what I mean, hertz. We get some incoherent mix of two different signals at the same time. A similar averaging effect happens with the formants. So if you took a signal with a strongly peaked formant, let's say at 500 hertz, and you took lots of signals with very strongly peaked formants at 500 hertz. So this time let's draw it as a function of frequency against, you know, energy or something. If you have some, let's say it's unvoiced sound, so there's no real periodicity. If you have some very strongly peaked sound, and it's around 500 hertz, some other very strongly peaked formant, sorry. So you've got all these things with strong formant peaks like this as a function of frequency, and you average them all. You don't get a strong formant peak at the average, you get a very broad, weak formant peak at the average. And the effect of that on the speech perceptually is typically that it becomes muffled. So just worth bearing in mind that this averaging can have negative consequences, even if all of the inputs that go into the average are exactly natural. And to put it another way, the data, the true set of spectrograms lies on a manifold, and averaging is taking us off that manifold to a point that's unnatural or physically unrealizable. And for spectrograms, you know, you have this effect, especially in the case of F0 and formants, that's bad. for waveforms, it's even stronger, even more clear. So you'd certainly expect for any piece of text that the average waveform, if you averaged loads and loads and loads and loads of instances of that same piece of text being read aloud, would be roughly 0 due to the phase variability. It certainly wouldn't be anything like the original spectrum, or original waveform, like any one instance of the natural speech. Okay, so yeah, not saying this is a disaster in all cases. Sometimes the output y might be sufficiently deterministic given x that this averaging isn't too bad. But anyway, just thought it might be, it's worth being aware of this potential pathology, and when you're thinking about how to design probabilistic models for different things. As an aside, this has actually been tried. So Gustav Henter with me and Tom Merritt and others actually tried, so made this recording of a time-aligned, made this recording of people saying the same thing like 20 times in a row, or 100 times in a row, I can't remember, and time-aligned them and then averaged them, and sure enough it sounds, so that's like the best that a model that inherently does averaging could ever do, or a deterministic model could ever do that's trained with L1 or L2, and it sounds muffled exactly as you'd expect. Okay, so moving on from non-probabilistic loss functions to probabilistic loss functions, we'll focus on the KL and reverse KL specifically. The KL divergence, just to define it, between the data distribution P and the model Q is KL P to Q. It's a kind of average of the ratio of the log ratio of the two densities. So we've got some sort of expectation here, the sum over x p of x, and then the difference in the log probs, or equivalently the log of the ratio. And if we're thinking about P as our data and Q as our model, then we don't really care about the P log P term. We can just absorb that as a constant, and what we get is minus sum over x P of x log Q of x. And that is just the expectation over the data of the log likelihood. So essentially it's the log likelihood with infinite data. So that's a link to maximum likelihood. Minimizing the KL is equivalent to maximizing the likelihood. And the KL divergence is large if P of x over Q of x is very large and P of x is not tiny. So that's important, kind of, both of those aspects are important. For the KL divergence to be large in a given region, P of x has to be not really, really small, because otherwise the whole thing will be 0 or close to 0. And P of x over Q of x has to be pretty big, because we're taking the log of it in order to get a large value. So the situation where this is really large, the situation that the KL divergence is trying to avoid at all costs, is that Q is tiny, tiny, and P is not tiny. It's something that could actually happen. Obviously these terms are rough, but yeah, that's the situation that KL divergence is really trying to avoid. In contrast, the reverse KL divergence, which is just the KL divergence from Q to P, but it's useful to have a different terminology for it, is large if Q of x over P of x is very large and Q of x is not tiny. So I'm using this notation kind of, which normally would mean Q is much greater than P, and here it means Q is much greater than P and Q is not tiny. So yeah, I guess roughly speaking anyway, the situation that KL divergence really tries to avoid is that P is tiny and Q is not tiny. And this leads to different behaviors if you optimize KL versus reverse KL. It's often called covering behavior for KL. The learned model distribution has broader support than the data distribution. And mode-seeking behavior for reverse KL, the learned model distribution has a support that lies within the data distribution. So let's see that with some pictures. In one dimension, the optimizing KL. So here the true distribution in both the top and the bottom is the blue double mixture of two Gaussians. And the model is a single Gaussian. And if you train this single Gaussian, so clearly the model isn't capable of capturing the true distribution exactly. If you train with KL, you get this kind of covering behavior where the model takes very large variance and it tries to cover everything that might happen in practice, even though it ends up covering some stuff that's quite unlikely in practice. So the value of the model here is much larger than it should be. And the model's aware of that, so to speak, but it can't make the value here smaller without leaving one of these high probability regions with no covering mass at all, and therefore there being a region where P is, it's always hard to get this the right way around, where P is tiny and, sorry, one way around or the other. The situation is reversed with reverse KL. So reverse KL is really trying to avoid situations where you could take a sample where there's some Q that could actually occur in practice, where Q is not tiny, but where the model says that's vanishingly unlikely. So it ends up with this mode-seeking behavior. So if we imagine flipping the two loss functions that we're optimizing, and we were trying to optimize the KL divergence, but found ourselves in the situation on the bottom, the KL divergence would say, this is a disaster. We've got to cover this mode here, because otherwise there's this region here of X space where P is much greater than Q, or vice versa. Conversely, the reverse KL would find itself in a situation, if it found itself in this situation, it would say that this is not great because there's this large probability region here. That doesn't seem like so much of a disaster. Anyway, it ends up working out that it's covering, that it's mode-seeking. Okay, let's look at a two-dimensional, yeah.
But when you have the KL, you don't need to know the distribution P exactly. You only need the data from that. If you want to optimize the reverse KL, you need a parametric form or whatever for the P.
Yep, absolutely. I'm definitely not trying to say it's just as easy to optimize reverse KL as KL. And as you point out, there's a simple sampled approximation to KL where you just take samples from P and optimize log Q on those samples. And there's nothing equivalent to that for reverse KL. You need to know P of X for reverse KL at arbitrary X's. And that's like, yeah, not easy to do in practice. So this is more just a theoretical kind of discussion. In practice, to optimize reverse KL, there are approaches. So the reverse KL GAN is one approach, which is an FGAN with a reverse KL divergence. You also might be able to, yeah, I don't know. I'm sure there are other approaches as well.
Variational also approaches are
Yeah.
for reverse KL.
Yeah. I mean, but there you're not, in that case you have Q on the left and P on the right, And that works because where you're optimizing Q, so you're optimizing Q in a reverse KL-like way, but you have access to the true P. Yeah. So moving on to a two-dimensional case, let's suppose that the underlying data distribution was this green 2D Gaussian, which is kind of not axis aligned, so it's got some covariance in the along the slope, and let's suppose we're fitting it with a isotropic Gaussian, or in general, just even if we assume just a Gaussian that is independent over the two different dimensions. So we have to end up with something that is axis aligned, meaning the kind of semi-major axis of this ellipse doesn't point diagonally, but points either in the y direction or the x direction exactly. So that's what you get if you assume that you make a independence over dimension assumptions, which is very commonly done for all sorts of modeling. This is what you end up with if you optimize reverse KL, and this is what you end up with if you optimize KL. And you can see that KL is putting a whole bunch of probability mass in regions that can never occur in practice. But KL says that's fine. What I really want to avoid is situations where the true model has some probability mass and I don't have any. Reverse KL is the opposite and ends up concentrating on the mode here, because reverse KL doesn't care about the situation where there's areas of space that it isn't ever going to generate samples in, but which occur naturally. What it cares about is that any samples it does generate, if you sample from this Q, i.e. if the Q value at a given point is not tiny, then the P value at that point must also be not tiny in order for the reverse KL to be reasonable. So yeah, this is another example of this covering versus mode seeking behavior. And finally, another 2D example with bimodal distribution, and you can see that KL has this kind of, again, attempt to capture both of the modes, just like we saw in the 1D case. The reverse KL has a couple of local minima, one fitting one mode, one fitting the other mode, and again, it's leaving all this probability mass out in the calls. So I've talked about this mode seeking versus covering behavior. Just as a little aside, actually the F divergences such as KL and reverse KL can be categorized more precisely than just this mode seeking versus covering distinction. And I'll just go through this briefly in case it's of interest to anyone, but no worries if it's not. The left mismatches, so let's define left mismatches as regions of X space where Q is not tiny and P is tiny. So Q much greater than P in my previous notation. Right mismatches are the opposite, where P is much greater than Q. You can actually define a notion of tail weight, and that captures how bad the left mismatches are. So if the tail weight is R, S, R captures how bad the left mismatches are, S captures how bad the right mismatches are according to the divergence in the limit of very large mismatches. So it's like if there was a really large left mismatch, if R is a large value, that means that the divergence really cares about that big left mismatch. If R is a small value, it means the divergence doesn't really care about that. So unsurprisingly, given all what we've seen so far, KL divergence has 1-2 tail weights, i.e. it penalizes the left mismatches a little and the right mismatches a lot. Reverse KL has 2-1 tail weights, so there's some symmetry there. It penalizes the right mismatches a little and the left ones a lot. Jensen-Shannon, which was used for the original GAN formulation, has 1-1 tail weights. So it penalizes the left and right mismatches evenly, but it doesn't penalize either one particularly strongly. I.e. it cares, it would if it had a chance to model one particular region of space a little bit more accurately, but that would mean having some very large mismatches somewhere else, the Jensen-Shannon divergence would be kind of okay with that, whereas the Kale or reverse Kale would say that's a disaster, we don't want to do that. So just different aspects to these divergences. And just as another example, the Jeffreys divergence, which is just the sum or average of the Kale and reverse Kale, has 2 tail weights. So it really cares about either left mismatches or right mismatches. So if R is greater than S, then the divergence is broadly mode-seeking. If S is greater than R, then it's broadly covering. But the absolute magnitude also matters. So the difference between Jensen-Shannon and Jeffreys, which are both symmetric, is that Jensen-Shannon is very tolerant of very large mismatches, either on the left or the right, and Jeffreys is intolerant. By the way, this left-right terminology is to do with the form of the way that f is defined, this function for the f divergences. It's not meant to be left or right in X space. Okay, so you can also show that the divergence is bounded if and only if these R and S values are less than 2. So Jensen-Shannon's bounded because both of R and S are less than 2, but Kale, reverse Kale, and Jeffreys are all right on the border of being unbounded. They're just unbounded, if you like, because they're equal to 2 and therefore unbounded because that's not less than 2. Okay, so just thought that might be an interesting aside. When you're talking about mode seeking versus covering, that's not really the entire picture. And indeed, people often talk about the original GAN formulation as being mode seeking, which is not really completely accurate. All right, so we've got mode seeking versus covering behavior. That's one way of viewing the distinction between Kale and reverse Kale. Another way is through desired and undesired variability. So if you take an imperfect model optimized by KL, it ends up not just capturing the variability that's actually present in the data, but also some additional variability which shouldn't be there just due to modeling, just due to modeling as noise, structure which is present in the data, but structure that the model can't capture. In other words, the noise parameters are really dialed up for the KL when you optimize the KL. By contrast, an imperfect model optimized by reverse KL, there's a missing reverse here, ends up not capturing the full variability present in the data. And in other words, the noise parameters, any noise parameters are kind of dialed down by the reverse KL. They're smaller than they really should be. And you can see this in GANs where samples lack diversity. And there's the original GAN loss, the Jensen-Shannon divergence effectively, that has these 1-1 tails and it's symmetric. There's an alternative non-saturating generator loss that's often used in practice. And that's actually effectively, when you're doing GAN training, optimizing or can be viewed as optimizing a mode-seeking reverse KL-like divergence. In fact, it cares even less about right mismatches than the reverse KL divergence does, because the reverse KL was 2-1 and this is 2-0, but that's not really a big distinction. The main thing is whether these things are less than 2 or not. Sorry, that's one point. And then you can also see in the green and red plot that modeling the dimensions as independent when they're not independent can have large consequences on the estimated variability. And we, at the very beginning, were discussing that this assuming things are independent when they're not is one way of dealing with high-dimensional data, but clearly can be a really bad idea depending on exactly the form of the data and exactly what you're doing with the model. So the mean in both these cases is pretty reasonable, and often that's what we care most about. But the variability is bad in both cases for reverse KL and KL in different ways. And so making faulty conditional independence assumptions can have bad consequences on the learned variability, I guess, is the high-level point there. Okay, so we've had mode seeking versus covering. We've had the desired and undesired variability. There's a third way to view the difference between KL and reverse KL that I think is somewhat informative, and that's compression versus sampling. So first of all, just to explain this link to compression, some of you might already be aware of, but there is one-to-one correspondence between codes and probability distributions. And by the way, if you're not familiar with this or you'd like to know more, the book by Dave Mackay that's mentioned here, Information Theory, Inference, and Learning Algorithms, does a really great job of going through this in lots of details, lots of practical examples. You know, at the end of it, at least for me, you become pretty convinced that there really is just, you know, they're basically the same thing, coding and probability distributions. There's really a very tight correspondence. So in this correspondence, the length of a code word in bits corresponds to the base 2 negative log prob. So you can, the one-to-one correspondence means that for any log prob, you can turn it into a code, and for any code, you're effectively defining a probabilistic model, as long as the code is decodable, which to some extent corresponds with the probability summing to 1 or being less than 1. Anyway, so because of this correspondence, the negative log likelihood, i.e. the KL divergence up to a constant, as we've seen, is just the average code word length when we use a code based on the model Q to compress samples from the true distribution P. So if we're in that situation where we've got samples from the true distribution, we're compressing it using a model derived from this, using a code derived from the model Q, then the average code word length, which is some notion of the rate or the efficiency of the code, is just the negative log likelihood, and the KL divergence is just the difference between the code length that our code has and the code length that the best possible code has. So thus, when you're optimizing KL, you're really optimizing the model for compression. And this makes sense intuitively, given these pictures that we've seen so far. If there's a region where P is not tiny and Q is tiny, which is heavily penalized by the KL, then at some point we'll encounter data which requires really long code words, because there'll be some sample from P where P is not tiny, Q is tiny, so log minus log Q is very large, so the code derived from Q uses a really long code word to describe these elements that aren't that unlikely under P, and that's bad for compression. You end up with a large contribution to the average code length because of that. By contrast, if there's a region where Q is sizable but P is tiny, then we waste a little bit of probability mass on for Q on possibilities that we end up never having to encode. That's not ideal, but it's not so bad for compression. So for instance, in this case here, if there's a whole bunch of stuff in this region that we have short code words for, but which never occur in practice because we're drawing samples from the true data distribution in green, then that's not so bad. You know, it's not great to have all these unused code words sitting around, but at least we don't ever have the need to use any really long code words frequently. In contrast, optimizing reverse KL ends up with models that have realistic looking or sounding samples. If there's a region where Q is much greater than P, which is heavily penalized by reverse KL, then we will sometimes encounter that region when sampling from the model. So if we take samples from Q, we'll end up at some point in this region where Q is likely and P is not. And that's the case even though those samples are really unnatural in the sense of having very low probability under the data distribution. So reverse KL tries to avoid that situation. and not have any regions where samples are unnatural, have low probability. And if it's the other way around, reverse KL doesn't really care. If it's the situation that KL would compress badly, where Q is much less than P, reverse KL says kind of I don't care too much about that. And that isn't great from the point of view of samples. If we think about it from a intuitive perspective, the samples will be lacking some diversity, since we'll not be modeling the model will not have captured all of the different things that can occur in the data. But each sample from the model will be natural, i.e. likely under the data distribution. And just to relate that back to this picture here, each of our samples from this reverse KL trained model in red is also natural according to the true data distribution, but there's a lack of variability because there's a whole bunch of stuff the model will never generate, even though the true data distribution does contain instances of those regions. Okay, so those are the three different ways of seeing reverse KL versus KL. I wanted to talk briefly about the implications of this for WaveNet and parallel WaveNet, and this is just kind of a random thought, not to. I mean, I'm not saying I have a lot of. Anyway, WaveNet is trained with KL, but despite prioritizing compression over sampling, still has samples which sound good. And that's interesting. That's not true of that many generative models. So a lot of models which are otherwise very impressive, very powerful generative models, GANs, especially GLOW and WaveGLOW, still for their best results require using a adjusted temperature sampling like 0.7 or 0.8 or something to get natural looking or sounding output. This was discussed briefly in Vasilis's lecture yesterday, that WaveNet is often capable of using a temperature of 1. I think that's really impressive. Whereas if you look in the back of the, in the kind of appendices for the GAN papers, the NVIDIA papers and the GLOW and WaveGLOW, and you look at the temperature 1 samples, they're kind of hideous or unnatural at least. And the fact that WaveNet is trained for compression effectively, but is still good at sampling, is interesting because it means it must be just a pretty good model, not too much covering or mode seeking, even though it wasn't trained explicitly to avoid to be mode seeking, or to avoid mode seeking. Anyway, so by contrast, parallel WaveNet is trained partly with reverse KL, which prioritizes sampling over compression. So even if the model was less powerful than WaveNet, sample quality might be partially being saved by the choice of loss function. And I just think that's an interesting thing to possibly be aware of. Even if the parallel WaveNet was a less powerful model, the sample quality would still be partially saved by that choice of a loss function that promotes good samples. That's the reverse KL. It would be interesting to investigate this, so you could easily tell by looking at the log prob, i.e. the measure of compression, how good, because the parallel WaveNet still has a tractable log probability, you could compute that log probability. And I would be kind of fascinated if anyone has some trained parallel WaveNets, and I should ask the folks at DeepMind as well. Whether the log likelihoods are good. They're not in the original parallel WaveNet paper. They didn't publish the log likelihoods. So it'd be very interesting to see whether the parallel WaveNet model is is like the original WaveNet model, powerful in terms of both compression and sampling. Okay, so to some extent, this KL-reverse KL dichotomy is something that I just feel like is underappreciated in machine learning in general, and that's one of the reasons that I wanted to share it with all of you. But it was specifically an aspect of how this relates to autoregressive models that I guess really made me want to mention it. And specifically how it relates to teacher forcing. So the KL divergence of an autoregressive model decomposes over time, and specifically the KL between P over an entire sequence X to Q over an entire sequence X is the sum over all times in that sequence of P of everything that's come before the current time T, and then the KL of the individual conditional distributions from P to Q. So this part is, extremely intuitive. This part, note that there's a P rather than a Q. So if we were to approximate this using samples, we end up sampling the previous, when we're trying to compute the KL loss at a given time step, we sample all the previous stuff from the underlying true distribution. So I've said that here, computing the KL contribution at a given time step takes the past history leading up to that time step from the data distribution P. And you can do a similar, we've seen throughout the talk that there's this parallel between KL and log likelihood. They're essentially the same thing up to a constant. You can do a even more straightforward decomposition for log likelihood. It's essentially just the standard, the log of the product rule autoregressive decomposition property that I presented originally. And the reverse KL is just the opposite of that, as you'd expect. So we just swap all the P's and the Q's, as it must be. And what that means is that we end up sampling at time step T all the previous outputs when we're trying to compute the loss at time T. We draw the previous outputs from the model distribution, i.e. non-teacher forcing mode. So KL, we end up doing teacher forcing, meaning that when we're optimizing the loss at a given time step, we take all the previous time steps drawn from the data distribution, and reverse KL, we end up optimizing using non-teacher forcing, i.e. we feed in the previous output of the model at time T in order to compute the loss just for that time step. So you can see in this view of reverse KL and KL, teacher forcing, non-teacher forcing, how an imperfect model trained with KL might generate poor samples. And this is kind of close to, a lot of people seem to not like the idea of teacher forcing very much and have an intuition that it might have negative consequences. And I think this is one way, anyway, of viewing that intuition. So at each time step, the model distribution is slightly broader than it should be because KL has this covering behavior. So each one step ahead prediction in the autoregressive model is slightly broader than it should be. And you can imagine that these slight differences have the potential, the model might recover or it might not. And these little mismatches that keep getting added each time might end up compounding because the model is autoregressive. And on the other hand, a model trained with reverse KL always sticks within the region that it knows is likely at each time step because it has this mode-seeking behavior at each time step. And so if the output at time T is within a highly probable region, then the conditioning input, which goes into predicting at time T plus 1, is conditioned on something that actually occurs in the data in practice. So reverse KL has this nice property that it kind of sticks within the region that it knows. At least a nice property if you care about sampling rather than compression. So Yeah, I personally feel like this is a nice formulation of the intuitive concerns people sometimes have with teacher forcing, which is something like this errors compound over time issue. And I just think this is kind of an interesting view because it suggests a principled but also probabilistic way of training autoregressive models which in order to generate good samples. And I like the fact it's probabilistic because that means you get variability in the resulting samples. So if you're just trying to predict a single value deterministically, first of all, you're at risk from this averaging effect that we discussed earlier. And secondly, you always get the same output. There's no way to capture variability in how people speak, for example. So I like the fact it's probabilistic, but then you're saying, given the choice between getting good compression, covering everything, and just saying, well, okay, I'm going to accept a little lack of variability. It'll choose that lack of variability. So just to make that a little more concrete, if it was in the situation where the model, was aware through to anthropomorphize, was aware that it couldn't cover everything, it wasn't powerful enough, it would, with reverse scale, just say, that's fine. I know I'm not going to be able to capture all of the variability in the true distribution, but at least I'm not just doing the mean here. I'm going to at least capture the variability within this one mode or within this limited space. So that's a nice aspect of reverse scale. So the intuitive issues that with teacher forcing also have been addressed with things like scheduled sampling. Ferenc Suzara showed that this was inconsistent, which is not that surprising. And he has an interesting paper on this and also advocates for reverse KL, how not to train your generative model. And yeah, anyway, I just think this is an interesting perspective. It doesn't mean reverse KL is easy to optimize in practice. I don't know the best way to do that, but I do really like the fact that it's both probabilistic, somewhat derived from a overall guiding principle, and likely to have, if we can do it, these positive influences if we care about sampling, which arguably for speech synthesis is exactly what we care about, not compression. And just as a partial aside, but I also just wanted to clear up this common concern that people have around teacher forcing, unlike the previous one, which in my view is justified. This one, in my view, is not justified, and that's that teacher forcing is somehow mathematically inconsistent, or rather using teacher forcing at training time and not at synthesis time is somehow mathematically inconsistent. And I think if we look at the sequence level, it's super clear that this is the right thing to do. At the sequence level, all we're doing is at training time, we're optimizing log Q of X for some sequence X. And at synthesis time, we're sampling a sequence X from Q of X. And if you think about a simple 1D Gaussian or something, and fitting that to some data and then sampling from that fit Gaussian, that's a very reasonable procedure that you optimize log Q of X, and at synthesis time you sample from that trained model. That seems very unobjectionable. And this is just the sequence level equivalent of that. So the fact that we teacher force during training just falls out completely mechanically from the fact that computing log prob in an autoregressive model involves teacher forcing. And the fact that we do non-teacher forcing during synthesis just falls out from the mechanical procedure that sampling from Q of X, sampling from Q of X for an autoregressive model Q of X involves non-teacher forcing. So there's really no other way it could be if you're using KL for training. Okay, so to summarize, training with non-probabilistic loss functions can result in some undesirable averaging. Optimizing KL versus reverse KL for an imperfect model results in covering versus mode seeking for KL and reverse KL respectively, too much, too little noise variability, or another way to view it, good compression and bad sampling, or bad compression and good sampling. The choice of KL implies teacher forcing during training, and optimizing reverse KL instead would mean non-teacher forcing during training and would prioritize sample naturalness in a way that optimizing KL doesn't, which is ultimately or arguably what we might care most about, but maybe hard to do in practice. Great. Oh, I've forgotten my questions, question mark slide, but are there any questions?
Well, we can discuss many hours for the loss functions, but my question is when the paper will be out? Your paper.
Say it again.
The paper.
Which?
You had your
The
Shannon
one where I
paper.
cited Shannon to be published or something?
Yeah, to be published. Yeah, this one.
Yeah. The GAN stuff. Yeah, it's all FGANs. Yeah, soon I hope. I've got a draft that I've been sitting on for like 6 months, and I should just publish it. I'm more than happy to share it, but even in its current rough form.
Okay. Can I make another comment? Sorry. There is also loss functions like total variation or Wasserstein or Hillinger, whatever. But another important advantage of KL divergence, either reverse or the original one, is that they are scalable for the autoregressive case. So this log of the product that becomes sum of the logs, this makes it scalable. So you can have also uncertainty bounds on this, on any quantity that you are interested in. So there are information-based bounds for uncertainty for any quantity of interest based on KL on the sequence level.
I'd be interested in learning more about that.
Yeah, sure.
Why don't we go halfway through, because I've got 5 sections, so it doesn't naturally divide the time anyway. Let's go halfway through the next section and then pause there, because it's a little bit of a dense one. So this is, the next thing I wanted to talk about was variational autoencoders. This is leading up to the use of variational autoencoders in tachytron, i.e. capacitron, but this section is just going to be focused on variational autoencoders from a general perspective. So variational autoencoders have a certain kind of minimal level of complexity, and I've tried to make the presentation as straightforward as possible while still covering all of the kind of important detail. Yeah, I think it's a really nice approach theoretically, at least, and often in practice too. Yeah. Okay, so variational autoencoders are a particular approach to making latent variable models more tractable. So as we kind of alluded to at the very beginning, very first section, a great way to make a generative model more general is to add unobserved latent variables. And that's also often desirable for plausibility, I would argue. For example, for a generative model P of Y, we might add a single latent variable Z, which you prefer. I'm torn having grown up in the UK and living in the States. Let's go with Z. So the joint distribution P of Y and Z is P of Z times P of Y given Z. So the generative model is kind of that we generate the value of this latent variable, and then conditional on that, we generate the value of what's observed. So at the risk of explaining things that are obvious 3 times, here is the equivalent graphical model. So we generate Z, and then we generate Y given Z. And this graphical model is exactly equivalent to saying that the joint distribution between Y and Z is P of Z times P of Y given Z. In this model, the Z is unobserved, and so I've not shaded that node, and the Y is observed. So I've shaded that node, and that means what we actually observe is just P of y. So the the latent variable only has consequences for the things that we actually observe through the way it affects the distribution over y, and specifically the ultimate thing that we can that we actually the distribution over the thing we observe, P of y, is just the sum over of P of y and z over all possible z. So that's referred to as the marginal probability. And there's some common terminology which is not the best, but is somewhat helpful for these different pieces. P of z is commonly called the prior. This is by analogy with a kind of more variational Bayesian approach where the prior was really a prior over parameters. You can still kind of view it as a prior in this case. And then P of y given z is referred to as the decoder often. Great. So latents were great from all sorts of perspectives, in particular generality and plausibility, but for attractability, they're not so great. And adding latents complicates inference and training. It typically makes exactly optimizing the KL, the marginal KL, the KL of that P of y intractable. So there's variational autoencoders or variational lower bound methods or variational free energy methods are a trick for making inference and training tractable. And the trick is that you add an auxiliary probabilistic model Q of z given y, and that's referred to as the variational posterior, also referred to as the encoder. And you want that to approximate the actual model posterior P of z given y. So if you took not the true distribution, but your model, joint distribution over z and y, condition on the y to get the posterior according to the model, you're training the variational posterior to be close to that generative posterior. And if we look back at the way that P of y and comma z was defined, it was defined in terms of z and y given z. So in order to compute the probability of z given y, we have to do some marginalization and normalizing and stuff. So just to say P of z given y is not a trivial quantity to compute, and that's exactly why we introduced the variational posterior. If we could compute this tractably, then we could just use it directly. The really nice aspect about doing things in this approach is that there's a single cost function which you can use to optimize both the generative and variational parts of the model. So here I'm using the terminology that PT is the data distribution, and in the previous section on reverse KL and KL, I was using P for the data distribution, Q for the model. Now I'm using PT for the data distribution, P for the generative part of the model, and Q for the variational part of the model. So apologies for the confusing switches, but I just, it seemed more straightforward to keep it. Yeah, there's a single cost function which can be used to optimize both the generative and the variational parts of the model. And that cost function is as follows. So I think I have that repeated. Yeah. So let's break this down a little bit. Here we have two joint distributions over y and z, one on the left, one on the right, and we're trying to make them close to each other. On the left, one way of looking at probability distributions is to look at how you generate samples from them. So in order to sample from the joint distribution over z and y on the left, you would sample first a y from the actual true data distribution, and then this should be z, sampling a y, then a z, yeah, and this is wrong too. Okay, so it consists of sampling a y from the actual data distribution, and then sampling z given y. So first of all, we sample y, then we sample z. Oh, that's correct, sorry. And then on the right, we sampling from the sampling from this distribution on the right consists of first sampling Z, i.e. sampling from the prior, and then sampling Y, and this is wrong. Okay, so it's that and that where the mistakes are. Y from the decoder. So just looking at this expression, to sample from the left, you're sampling Y and then Z. To sample from the right, you're sampling Z and then Y. And so we've got these two kind of forms of model, and we're optimizing the KL divergence between them to be similar. And I'd say it's intuitively somewhat reasonable that optimizing Q and P to make these two distributions close to each other is a good idea. In particular, for example, if the KL between these two is 0, then it's easy to show that the marginal distribution, in that case, P of Y, which is after all we really observe, or all we influences anything we observe, is equal to the true distribution over Y, and that the variational posterior Q is equal to the generative, the actual variational, actual model posterior derived from the generative part of the model. So in the case where this divergence is 0, all of these different pieces, the variational piece and the generative piece of the model, interact in a way that it's just behaving like one big generative model. It also makes some sense intuitively, I feel like, that I guess just that these are two different ways of decomposing a joint distribution over Z and Y, and you're kind of trying to get those two joint distributions to be close to each other. Yeah.
Can we say that the first term is the encoder part and the second term is the decoder?
Yep. So the Q is often referred to as the encoder, and the P of Y given Z is often referred to as the decoder. So it's this part specifically that's the encoder, this part is the decoder, that's the prior, that's the data. So in addition to being somewhat intuitive, this has extremely nice mathematical properties, and I think it was the mathematical properties that were really discovered first. For example, you can take this and decompose it into two terms, one of which is this, and the other which is another KL divergence. In fact, the KL divergence between the variational posterior and the true posterior. And that shows, because KL divergence is always positive, that this KL divergence on the left is greater than or equal to the KL divergence on the right, with equality only if the two posteriors, the variational posterior and the true generative model posterior, are equal. And this is kind of nice because this thing on the right is what we actually wanted to optimize. It's the KL for the marginal distribution over Y, which was intractable. So the cost function, which is the thing on the left, is a lower bound on the overall marginal KL divergence. Upper bound, right? Upper bound, which is what we originally wanted to optimize but couldn't. And as I mentioned, you get equality if and only if the variational posterior is equal to the actual posterior, generative posterior. And a nice property, another beneficial mathematical property when you're optimizing using this is that for the optimal variational posterior, not only is the value of the left-hand side equal to the value of the right-hand side, but the gradient of the left-hand side with respect to the generative or variational model parameters is equal to the same gradient of the right-hand side for the optimal variational posterior. So in summary, the variational posterior can be seen as a trick to allow tractable training and inference in models, latent variable models that would otherwise be intractable. So that's my kind of high-level, but still involving some detail overview of variational autoencoders. This is a little different from how variational autoencoders are normally presented. They're normally presented in terms of wanting to optimize the marginal log likelihood rather than the marginal KL. As we've seen, the marginal KL, marginal log likelihood, or log likelihood and KL in general are basically the same thing, that they're only differ up to a constant. And I think including that constant just makes for nicer expressions, writing things in terms of the KL, but that's a matter of opinion. And the normal way of formulating it is evidence lower bound, meaning a lower bound on the marginal log likelihood is what you're optimizing, rather than an upper bound on the KL, but they're equivalent. So yeah, just a rewrite, and in the lower bounds, more conventional way of describing this, this is a picture taken from the Bishop book. This picture is actually applying to the EM algorithm, but the maths for this aspect is essentially the same for the variational autoencoder. So this gives some intuition about what the variational autoencoder is doing. So here we've got in red the true marginal likelihood, in my notation log p of y. This is as a function of the generative model parameters. So theta here is the generative model parameters. And for any given choice of the variational distribution, which is Q, both in this slide and in my slides, for any given choice of Q, you get some lower bound as a function of the generative model parameters on the true marginal likelihood. And that lower bound touches at the if Q is optimal for a given theta. So for each different setting of the generative model parameters, there will be a different optimal variational distribution Q, because it has to be the variational posterior, and the variational posterior P of z given y depends on y. Depends on the it depends on the generative model parameters anyway. So for each different setting of the generative model, you get a different, for each different setting of Q, the variational posterior, you get a different lower bound. And these lower bounds can be typed sometimes depending on the form of model. And as you're optimizing the generative model, you also, let's say you're moving from the blue situation towards the green situation, you're also updating the variational distribution, so it kind of tracks ideally the optimal variational distribution. Okay, let me just pause there for questions, because that is obviously a lot to take in if you are not already familiar with this. So any high level or general questions?
I'm new to variational autoencoders, so I don't know if my question is stupid, but how hard is to condition these models into high level stuff like speaker identity, and how hard the encoding would be, in the sense that, let's say I have a data set of, 3 speakers, and maybe only one of them has certain prosody. If then these models kind of they sample, right? So they could I get a sample from a different speaker that shouldn't belong to the right speaker? I don't know if that makes sense.
So I guess one generative model might include, there's a few different ways of incorporating speaker. So let's say you have this generative model where this is some latent to do with prosody, and that influences the audio. So we've got text, spectrograms, and some latent, fixed dimensional latent encoding something about the prosody. And then you could condition on the speaker if you always know the speaker labels, or you could have a latent variable if what you observe is just a whole bunch of data and you don't really know You might get data from a new speaker, or you don't know the speaker labels. So let's call that S. And I think your question in this kind of framework is partly about whether there should be some sort of arrow linking Z and S here, or whether there's some correlation between the prosody embedding and the speaker embedding. And I think it really I guess designing a good generative model would require, examining some data, seeing whether this, you could imagine it going either way, I guess. You could imagine that, for instance, that let's say that certain speakers have higher average F0 than other speakers. In that case, you could imagine that if Z was just encoding average F0, you wouldn't really be able to capture that in a model like this. But if but what you could capture, and what the model would end up learning to do, is just capture the kind of relative F0, whether it's high or low, for that speaker in Z. And then the decoder would figure out that, if you have a speaker with a low average F0, but this Z is pushing them up, then, you get a bit higher, and, the similar thing for someone with a high average F0. So, I guess my only useful point is that this kind of drawing the generative model is a helpful way to think about it. But that is very much on the plausibility side for me. And this is about designing the good generative model. And that's not easy, but what's nice is if the tools are flexible enough, however we think it should work, to allow us to implement that. And the variational part of this model would look much the same for any of these different graphical models. In all cases, you'd get some joint distribution, variational distribution over Z and S. Any other questions?
There is here a question from a person who follows remotely. So,
Cool.
So they say that whether the variational autoencoders can at the end find more than one mode, or just the main one?
So the mode seeking versus covering behavior of variational autoencoders depends on whether you're talking about the variational posterior or the generative part, because the variational posterior appears on the left side of the KL, and therefore you're essentially optimizing it using a kind of mode seeking behavior, and the generative model is still on the right part of the KL, just like it would be for the non-variational autoencoder setup, like any probabilistic model being trained with KL. And the generative part is still optimized using a covering-like behavior. What that means for the covering versus mode seekingness of the overall model, I think, is not straightforward. What you can say is, if you're using your trained model to do various forms of inference, you can work out whether that inference would have covering or mode seeking behavior. Like if you had a Y and you were inferring the latent, that inferred latent would tend to have a more collapsed sampling distribution than it really should, because of the mode seeking behavior. If you're using that inferred latent to then generate a new Y by sampling from the decoder, that will have too broad sampling behavior. If you're cycling through both the encoder and the decoder, then you're going to get bad behavior. Whether you care about sampling or compression, you're going to get one bad thing and one good thing. So yeah, hopefully that. So let's take just a very quick break now before we dive into the last part. So maybe like 4 minutes. Is that too ambitious? 4.2. Okay, so we discussed the evidence lower bound and kind of this intuitive picture of the evidence lower bound. There's one remaining mystery that I wanted to describe, which is why variational autoencoders are called variational autoencoders. Why use the word autoencoder at all? And this stems from the form that training takes in practice. So the cost function up to a constant is given by this expression here. So this just comes directly from the expanding the previous slide. And since we're using stochastic optimizers such as SGD for training, it makes sense to just sample this Y and this Z and get a single sample unbiased approximation for each utterance, namely this, where Y is an actual data sample and Z is a sample from the variational posterior Q of Z given Y. This is just that same equation represented again. And if the last true terms weren't there, we'd just have a normal autoencoder where we pass the data Y through an encoder to get a representation Z, and then pass that through a decoder to get a reconstruction Y, and try to minimize a reconstruction loss. And the first term can loosely be interpreted as such a reconstruction loss. And the last two terms can be interpreted as a sort of regularizer, a KL regularizer. So that's the loose analogy between conventional autoencoders and variational autoencoders, but it's not a precise thing, and there are important distinctions. But the analogy is that these two terms form a kind of regularizer. This is like a reconstruction loss, and the procedure that we do to compute this reconstruction loss is just pass the observed value through the stochastic encoder, then through the stochastic decoder. But there are important distinctions, and to be honest, I think variational autoencoder is not a great name for that reason. Variational autoencoders are, very roughly speaking, trying to do something more like ensuring the distribution of the reconstructed outputs matches the original distribution, whereas conventional autoencoders are trying to ensure that individual samples or examples match the original. So there's actually no reason for variational autoencoders to do autoencoding at all. If the decoder is sufficiently powerful to model the output without using a latent, you actually see this in practice. The decoder just learns to ignore the latent and no information is passed through this reconstruction process, but you still have a very good generative model. So the encoder will just output some random garbage, the decoder will ignore it, and the final output is the same no matter what the input to the encoder-decoder stack is, but the output is still drawn from the right distribution, so it gets a perfect cost function value. And from a generative modeling perspective, that's fine. If the model learns to ignore the latent, as long as all we care about is the accuracy of the final generative model, that's not a bad situation. But it means it can't really be viewed as an autoencoder because it's just matching the distributions, not the individual examples. So just wanted to explain the name given that I've been using that name throughout. There's another important detail with variational autoencoders, which is important to get stable training, and was really one of the keys to making this all work when there were like 5 papers that came out around the same time, around 2014, all with basically the same idea for this variational autoencoder. And one of the real keys to getting this to work was the reparameterized gradient. So we saw before on the previous slide that we can approximate the value of this objective function, which is just the elbow, by using a single sample z. But you can't approximate the gradient that way because you're taking the gradient with respect to the parameters of Q, and that both affects, so the gradient passes through both this term and also this term, the thing you're taking the expectation of. So you could do a kind of reinforce-like thing where you end up manipulating the gradient in order to get a still the expected value of some quantity, but something that works much better in terms of reducing variance typically is to reparameterize Q so that Q is an invertible deterministic, or Z rather, is an invertible deterministic transform of some fixed distribution latent variable. So for example, if your Q is, you want it to be Gaussian, you could take some W, which is a normal 0, 1 Gaussian, transform it using some learned mu and sigma to get the final output Z. And now this expectation, instead of being over Q, is over the distribution of W, which is fixed. And so you don't have to worry about the taking the gradient of this with respect to the variational model parameters, because all of those variational model parameters are already incorporated in the dependence of the Z used in this part of the expression on mu and sigma. So this is an important detail. Luckily, you don't have to worry about this much in modern libraries such as TensorFlow probability, and hopefully we'll see how easy that is. Variational autoencoders are to implement in TensorFlow probability this afternoon. It's quite nice. And just to link back to our earlier discussion of strengths and weaknesses of different models, let's just take a look at the properties of VAEs. So firstly, note that what properties we need from the various distributions. So we need tractable sampling from Q of Z given Y. That's important there. We need tractable log prob for Q of Z given Y on those samples. That's important for this term. We need tractable log prob for P. That's important for this term. And tractable log prob for P of Y given Z, the decoder. So a whole bunch of tractable log probs, one tractable sampling. Q is the only thing where we need both tractable log probs and sampling. So in practice, all of these distributions are often modeled using independent over dimension models. So for instance, Gaussians with diagonal covariances. And that certainly satisfies all of these tractability requirements very well. And the independence over dimension for the generative part is not too problematic, as I alluded to in the first section, because the complicated correlations in the marginal can be induced just by making the dependence of P of Y given Z on Z a complicated neural net. And we know how to do that complicated stuff for the thing we're conditioning on just using RNNs, CNNs, whatever. But the independence over dimension for Q of Z given Y is more problematic. I at least would expect it to be very difficult to come up with a model, a true generative model, which is both independent prior, independent decoder, and independent variational posterior, where independent means independent across dimensions. And if we don't have the property that the variational posterior is capable of matching the generative true posterior, then kind of all bets are off in terms of the gradient being useful. In the Bishop view, this lower bound is no longer tight, and you might hope that the gradient would point in the right direction, but there's really no reason to think that it necessarily would. So I think this might be, a bit of an issue for the current crop of VAEs. There have been attempts to alleviate this. You can use generic universal tractable models like the mixtures, autoregressive models, or flows for Q of Z given Y as a way to add flexibility. And you do indeed observe practical benefits from that. So Kingma had this paper on improving variational inference with inverse autoregressive flows. I have also observed a big improvement in latent space sometimes by just moving from a diagonal to a full covariance Gaussian. So even a simple change like that allows the model to have a better latent space because the variational posterior comes closer to capturing the true generative posterior. All these generic universal tractable models may end up requiring more parameters. Maybe we don't really care about the number of parameters for Q or the plausibility of Q because that's just a tool, or maybe we really want it to reflect. So that's up for debate. But maybe my bias is that I kind of like the idea that Q would reflect, would not just be a general purpose universal tractable model, which we have to use loads of parameters for. It'd be nice if we could do something that made more sense for the individual distribution. But anyway, summarize for variational autoencoders, adding latent variables can help improve generality and plausibility, but hurts tractability. Adding a variational posterior is a way to get around this. The new objective is an upper bound on the original training objective. Exact value and gradient values when the variational posterior is exact, and you get independence over dimensions. Independence over dimensions for the variational posterior is commonly used, but can lead to poor latent representations in some cases. So any questions about variational autoencoders, part 1, the theory? Let's move on to part 2, the practice. So capacitron, and this is my final section, capacitron is a model that combines tachytron and VAEs. So in this latent variable model, we have the normal tachytron plus this new latent variable. So normal tachytron would just be x going to y, and this new latent variable z feeds into the decoder and is marginally independent from x. And we're going to use this latent in a way that captures something related to prosody or a speaking style. So the latent variable is intended to represent intonation, stress, or rhythm, which could loosely term prosody. Just to mention, this builds on a lot of previous tachytron work, so I'm going to just describe this stuff using variational autoencoders, so a very probabilistic approach to modeling prosody and style. But there's been lots of previous work by the tachytron team on prosody manipulation using other approaches. There's some cool demos. This model comes in low capacity and high capacity variants, where the capacity refers to how much information about the audio the latent is allowed to store. So high capacity means that the latent can have lots of information about the audio. Low capacity means it can't have much. And the approach that's taken allows you to explicitly control that capacity, which is kind of a nice approach. In a kind of more standard formulation, the capacity would be controlled, or the amount of information in the latent about the observed would have to be controlled by modeling choices. So assuming things are independent, meaning that the latent is forced to capture certain aspects, certain correlations that the model, that the decoder couldn't capture on its own because of its independence assumptions. So for the low capacity variant, the thing we expect to be captured by this latent is utterance level aspects of prosody. It's like, is it generally expressive? Is it fast or slow? High F0 for a given speaker, or low? And for the high capacity variant, it's got enough dimensions that you start to see it capturing some time varying aspects of prosody, which may be a good thing or a bad thing depending on your application, but you have the control. So for capacitron, the variational posterior is Q of Z given Y and X. And even though this generative model has no explicit link from X to Z, because of the way that graphical models work, if two nodes share a child, then the true posterior has a link here. So probably we should have our variational posterior having a link as well. So we need to make the variational posterior ideally conditioned on both X and Y. not just on y. The paper actually investigates what happens if you don't do that correctly, and if you just condition the variational posterior on the audio y, but not on the text. Sure enough, you get a poor latent representation, particularly high capacities. It really breaks style transfer. Style transfer doesn't work very well anymore when you use this incorrect latent assumption. The paper does still assume independence over dimensions for Z, so within Z it still has this faulty independence assumption. But hey, you can't do everything at once. This is just a diagram from the paper showing the generative model and the different forms of variational posterior, a good one and a bad one. The generative model here also incorporates speaker, so similar to the one that I drew for the discussion earlier. So we've got text, audio, or spectrogram, latent, and speaker. So they've X and Y are the other way around in this paper from what I have used. Okay, so let's say we've got this latent variable. It captures some notion of speaking style. How can we use this trained model for style transfer? So the procedure is to infer the Z, the latent, for a source utterance by sampling from Q of Z given Y and X, sampling from your variational posterior, where X and Y are taken from the source utterance. And then you take this Z that was inferred from that source utterance and use it to generate audio for a given text on the target utterance. So the source utterance used both the text and the spectrogram, and the target utterance used just the text because you're trying to generate the spectrogram. And the latent is inferred on the source and then reused for the target. This form of style transfer only really makes sense for the form of graphical model that we've used. For instance, if there was a link from X to Z here, you wouldn't really be able to take the Z for one utterance and reasonably use it and meaningfully use it on a new utterance, because that new utterance would have some other X. And so there's no reason to think that the pair of X and Z is plausible, is reasonable once you've transferred the Z. Whereas the fact that X and Z are conditionally independent in this model means that you can take the Z for one X and reasonably use it for another X, because the model has been trained to have that that independence, sorry, marginal independence property. Okay, any questions about that high-level transfer side of things? Great. I just wanted to describe a little bit of detail about the, let me just check that I'm, yeah, that's pretty much it. Great. A little bit of mathematical detail about the this notion of capacity that the model formalizes. There's a common VAE variant called the beta VAE, and that's to simply take the standard VAE objective, which the single sample version looks like this, as we've already seen, and it adds a weighting term. So it groups these last two terms together and multiplies them by some weight beta. If beta equals 1, you get the original objective. One way to view this modified objective with beta is as a Lagrange, viewing beta as a Lagrange multiplier. And in this view, what we're effectively optimizing is the standard VAE elbow objective, subject to a constraint on the average value of this second term, the term that's multiplied by beta, because that's the kind of Lagrange multiplier general formulation. And this second term has an interesting interpretation. The average value of those last two terms is over all y and z, so rather than a single sample and just the kind of expected value, is given by this. And if we remember the definition of KL and add in a PT here and a PT here, that's just equal to the KL between these two distributions. This isn't the same as the elbow. It's missing a term, so it shouldn't be. But it's actually a form that looks very much like the mutual information. So, Lagrange style optimization, this beta VAE is optimizing the elbow given a certain value of this quantity. The mutual information between y and z under this distribution, which is based on the true data, it's sometimes called the representational mutual information as opposed to the generative mutual information. I think that's Alex Alemi's term, probably. The mutual information takes this form, where Q of Z here is what's sometimes called the aggregate posterior, which is just kind of the average value of Q of Z given Y over all different Y in the data. If we compare these two forms, they're extremely similar. In fact, the only difference is P of Z here versus Q of Z here. And in fact, you can show that the top expression is an upper bound on the representational mutual information, this second expression. So since it bounds the amount of information, this mutual information between Z and Y, since the top expression bounds the amount of information the latent Z can contain about the spectrogram Y, we refer to the top expression as the capacity. It's an upper bound on the mutual information, representational mutual information. So for each choice of the Lagrange multiplier beta, we get a different value of this capacity. So we could optimize, do the whole optimization fixing beta, getting lots of varying values for the capacity as training progresses. But it'd be nice to be able to set the capacity because the capacity is a more intuitive quantity than beta is probably. So we could say, for example, I want to only allow 10 nats of information about the audio to be encoded in the latent. That's kind of a cool thing to be able to do during your training. And capacitron describes a dual optimization approach that accomplishes this, allows you to set the KL target, the capacity, and essentially it decreases the beta if it's found to be too high and increases beta if it's found to be too low. So it's super simple. It's very simple. I implemented it just a couple of days ago, and it was very easy. And it's really nice. You just get these nice curves that level out at some point to the correct or the desired capacity. And beta, whereas now the capacity is constant, beta is changing over time, training time. And anyway, just really nice approach, simple to implement in TensorFlow. And the capacitron paper also compares against some previous non-variational methods of style and prosody transfer. And I wanted to end by just playing you a sample from the paper because it's kind of fun. Hopefully the audio will still be. Oh, doesn't seem to be working. Anyone have any immediate ideas? Otherwise, I can just play you this afternoon.
Yeah.
Oh yeah, it's on.
Should be.
Yeah.
Have you muted?
Not in that way.
Cool. So let's skip to the fun stuff. Single speaker inter-text style transfer is a good one. So
Not in that way.
is the reference.
And the distinction is not quite so much against the candor and common sense of the world as appears at first. And the distinction is not quite so much against the And the distinction is not quite so much against the candor and common sense of the world. And the distinction is not quite so much against the candor and common sense of the world as And the distinction is not quite so much against the candor and common sense. And the distinction is not quite so much against the candor, not in that way.
So you can see as we increase the capacity, these C is the capacity values, we get more and more aspects of the source being captured or being transferred across, being captured in the latent and therefore being reused. So a particular fun one is this one.
That's right, shouted the Queen.
So that's the reference. That's a real natural audio recording from Catherine Byers, if you can believe it.
Chapter 1.
And there's a very nondescript, neutral utterance that she's reading. And so if you transfer the outrageous prosody that you get for this very kind of expressive source sentence onto this target text that's very neutral, you get some good results.
Chapter 1.
So that low capacity, not too much difference.
Chapter 1. Chapter 1. Chapter 1.
You start to get a little,
Chapter 1.
starts to get more expressive, more and more like the source.
Chapter 1.
And just to show you the fact that modeling the having the correct structure for the variational posterior, having that dependence on the text in there, not just the audio, is important. The V system here is not doing that properly. It's just conditioning on the audio for the variational posterior, and you can hear it sometimes breaks down.
Chapter 1. Chapter 1. Chapter 1. Chapter 1.
So that case actually just is extremely expressive and works well. Let's try one other.
He left them carefully He left them carefully closing the front door. He left them carefully closing the front door. He left them carefully closing the front door. And they left it all into this and walked the drive and be in front of the slopes of within found behind the house.
So arguably that's garbage. This one in particular will be garbage.
Yet he might not have been so perfectly humane. He might not have been so perfectly humane, so only to not be so like an
All right, I'll end with that.
Then the next column, please.
Oh yeah, this one, sure,
Yet he might
absolutely.
not have been so perfectly humane, so thoughtful in his generosity, so full of kindness and tenderness. Yet he might not have been so perfectly humane, so thoughtful in his generosity, so... Yet he might not have been so perfectly humane, so thoughtful in his generosity, so full of... Yet he might not have been so perfectly humane, so thoughtful in his generosity, so... Quick now!
So arguably it does capture the aspect of speeding up, but the speeding up is relative to the length of the text, and presumably the reason that it gets it wrong in the other case is that it doesn't know the length of the source text, so it can't condition on that and adjust to make the kind of speed relative to the length of the utterance.
So is that the paper in July? That it's
Yeah.
a second version of it? July 9th, 8th?
Yeah, I think,
Okay,
well,
that's
I could be wrong, but I thought the second version's pretty, just minor changes. Things like
okay.
mentioning capacitron in the abstract,
Okay.
which is a good idea.
Okay, thank you.
But, yeah. Okay, that's it.
Where was that last sample from?
Like all of those samples are from Catherine Byers, who's a particular speaker, was recorded by Lesac before they went bust. But was that your question, sorry?
Yeah.
Okay. It's the same speaker that was used for the Blizzard Challenge 2013, I think. And she's quite an expressive, as you heard, very expressive speaker. Yeah.
That's the audiobooks for kids? Or before that, probably?
I don't know.
Right, anyway.